So welcome from the University of Stuttgart. As you know, the University of Stuttgart, or the HLRS, is within the work package for visualization. So our TNA projects were more kind of an implementing project supporting the visualization of data sets from our project partners or guests within Visionair. So far we have 3 TNA seminars, 3 TNA projects finished. This week we have the 4th one, so we are quite working on that. So these are the short names of the project. So just starting with the first one, and this is called Evaluating a Nested High Resolution Weather Model. And our guest was Sean Delaney from the Irish Centre for High-End Computing. And a little bit about the background or what they are doing there. So the Computing Center is working on modeling tools and simulation methods to evaluate coupled weather models. So specifically they have a small bay, the Galway Bay there in Ireland. And this is also called the Smart Bay because this bay is equipped with numerous sensors, for example, water temperatures, wind speed. There are a couple of radars installed there to get the clouds, to get information about how much it is raining there. So there's a very large set or network from sensors all over the bay. And this bay is very interesting because there are many inlets there, many small islands, and for that they have to reduce or increase the resolution of the weather models, going down, I think there was down to 100 meters resolution of the models there. And within their project coupling weather models, they have a coupling of sources. For example, they have Harmony, ROMs, and this one is called DVAST. They are working in different resolution, providing different kind of sensor data. And with these data sets, they are starting their simulation to get a good weather prediction of the surrounding of the Galway Bay. So the goal of the project is, as I said, the coupling of the data sets as well as the comparison from the simulation to the observed data, and the numerical problems, or just going in the numerical problems. There's the problem if you just have nested data sets, so you have a high resolution data set coupled within a low resolution data set, you get some numerical problems like shock noise or energy build-ups where the both data sets are coupled together, so on the boundary of the data sets. And the main goal to achieve is just getting better prediction of extreme events in that bay. So the more technical challenges we have are just how to get the data sets inside CoVis, our visualization software we have here at HLRS. And of course we have to integrate multiple data sets to CoVis in different non-Cartesian grids. So the problem is just that the sensors are not regularly arranged, so we have trying to read the data sets, map or register the data sets on each other, and then we have to connect them. Then of course for the researcher himself, it is very interesting to get all the nets through a visualization, so then he can just choose through the numerous variant of parameter sets of sensor data, for example, to do a visualization of the wind within the ocean current simultaneously, and just to switch between the multiple simulation data. So what we achieved, of course, we gave introduction and training to the researcher into CoWISE. We integrated the NetCDF library, so this is the library the datasets, sensor datasets are using to write out their data. So we implemented a new reading module to read NetCDF files. And of course, because the datasets are very huge, again, so we have huge datasets of sensor data. For example, one dataset was about 400 megabytes, and we have a couple of them, and just try to read them. So we're doing a little bit of optimization of the reading module just to be fast enough so that we can use it within the cave. And then, of course, we did a first visualization with the researcher with the integrated data sets. You can see on the right side. So we have, for example, in the top of the data sets, there are an isosurface representing the landscape of the bay, and under that we have the temperatures and some currents, wind currents. Okay, they are underneath the surface, but the idea was just to change between the data sets and mapping or registering the data sets on each other. Yeah, and of course the researcher, the computing center in Ireland now uses CoWISE, so we are giving support to them, giving support to the installation, so they were up to install CoWISE in an virtual reality setup with head tracking and so on, and we get support to them so they can now use CoWISE and do further implementation of the NetCD reader. So the next project was called Evaluating the Turbulent Incompressible Flow and the Particle Tracking in the Axial Cyclone. This is a German word, it's hard to find an English word for that, with high resolution model. So our guest researcher was Markus Lenarczyk from the Institute for Energy System and Thermodynamics from the Vienna University of Technology, TU Wien. And they are actually working on, for example, turbines for water power plants. This is very interesting for Austria because they have a lot of possibilities to install and set up water power plants there. But they have a huge problem because the water is very or comprised of sand and particles in the water getting inside the turbines. So they have the problem that the turbines are damaged, or the turbine blades are being damaged by all the sand, and damaging the turbine blades leads to unbalanced running of the turbines. This means more turbulent flow, water flow to the turbine, noise, and of course a lot of damage to the mechanical system of the turbine, which then means that the turbine has to be shut down. This costs money, costs time just to repair it or replace it. And so they came up with an interesting idea. So they are, actually this is a patent from the TU Wien, so they are in the process to optimization the axial cyclone. The idea of the axial cyclone is just to clean the water which is tend to go inside the water turbine from the sand without any moving mechanical parts. So we have this setup. So this is the actual design, and the water is going from the top left side into the axial cyclone, and by these blades you can see here the water gets in kind of a rotating movement. So the water is just getting in a rotation, and we cannot see them here, but there are some kind of little holes in this part of the mechanical construction, and by the rotation of the water, the particles are pressed to the outside of the tube and then separated from the main water flow, which then continues going through the water turbine. So the sand goes out here somewhere through the hole, through the separators, and 90% of the sand and the rest of the water with some little sand particles is going to the turbine generating energy. So the goal of the project they are working on right now is just to, of course, evaluation of the simulation data and to improve the construction and the design of the axial cyclone, and trying to do a little bit of optimization of the separators. So the challenges for us were again the huge data sets, because they are, as mentioned in the title, they are simulating that model in high resolution. So the data sets we had to read in were about 1 gigabyte. So this is even for a visualization cluster, it's a huge data set. So we had to improve our CFD reader module for this data set, so we don't have to wait for a couple of days, just for a couple of, the largest one takes a couple of hours, I think there were 2 or 3 hours, just to load it. And then we had something like a conversion tool that stores the simulation data in a co-wise intern data format, which can then be loaded within a couple of minutes. Yeah, as I said, so we are loading the visualization information, and of course they are interested in steady and non-steady states of the simulation and the comparison between those. And what was another important point for them was just they had numerous of parameters in the simulation, and for the visualization they need just to switch between the parameters, map different parameters to the visualization, just to get better understanding how the axial cyclone is working and how it can be improved. So the results look a little bit brighter in our new cave, I think. So again, we gave introduction and training to the researcher using co-wise and OpenCover. And again, the researcher or Theo Wien is getting a co-wise license, so they can use co-wise at their own place, getting support, further support, and installing and implementing co-wise modules. And what we did and what we accomplished was to improve the read CFD module, so that these huge data sets, or the system itself, is capable of reading these huge data sets. And again, we are realizing first visualization and animation of the simulation results, you can see on the right. So what you see on the right is just the entrance of the axial cyclone entering. So the water flow is coming from the left side, entering the axial cyclone. These are only the traces and the particle traces. So now geometry right here. Can you see that in the next slide? So on the left you see a cutted geometry of the axial cyclone. The water inlet is on the right side, you can see it here. And as I said, the particles are getting, or the water is getting, in a rotation movement for this one. And on the left side you can see the separators, so about 90% of the particles, of the sand particles, are being separated from the water flow going through the axial cyclone. On the right side you can see a nice picture from inside the axial cyclone, just the both guys standing in there watching the particles and the separators. So the next TNA is called 3D airflow and heat exchange visualization of a server room under various load scenarios. and our guest was Wojciech from the supercomputing department from the Potsdam Supercomputing and Network Center. So this is not our partner in Visionair, but this is another department there concentrating or doing work in the supercomputing methods. And what they are working right now on a project called Cool Them All, which is funded by the European Commission also. And within that project they are working on a design tool, a simulation tool and visualization tool to do analysis of the airflow within the server rooms, the air conditioning system, how the specifically servers are running under what load, and how the cooling system has to be set up so that the cooling is quite energy efficient. So the goal of the project is to implement a simulation, visualization and analysis tool for the designer of server rooms, so they are free to move the servers around in that room by a configurator tool, which is web-based, so they have the capability to move the servers around and to start a simulation, and then after that simulation has its first results, the web-based tool is doing some visualization. So you can see, for example, some heat spots where the heat is raising above limits, or some parts of the room are too cold, so that you can just save more energy in, for example, reducing cooling at that end of the room. So the challenges for our approach, so as I said, they are using a web-based visualization tool. So the challenging now was for within the project to support the project to bring that visualization not only on a web-based tool, but to bring that in a virtual reality space. So this was an interesting tool just to do a verification, a validation of their simulation algorithms and the tools they are using, just to understand if this simulation tool is quite doing a correct job or not. So they had just to bring their simulation data to a virtual reality setup or a visualization in 3D to get a better understanding of the results from the simulation tools they are using. So our challenges were that we had to adapt our interactive simulation tool we are using for this kind of simulations to their data sets. We had for since a couple of months we have a tool just wrote it for our computer room to get things designed in there, a better understanding how the air conditioning system is working. So we tried to adapt this simulation to their data. And then of course we had to model their server room with first of all an VRML modeler. So this was 3D Studio Max. So we started with the modeling of their server room as far as we get the information from them. And then we run a simulation. This was OpenFOAM. So on our visualization cluster, used as a simulation cluster this time. And of course, as we finished, we just mapped the visualization and simulation data, and we're going into our cave. So again, we just introduced our guest to Covise, how to use Covise and what he can do with it, give a little bit of introduction and training to him. And then we did the modeling of the server room. This is quite huge scale, so problem, so we have to refine the module a little bit so the outlets are correct, and yeah, so the researcher has to continue his work with more details, or adding more details to the model. Then we had the data which came out, the project are in PLM XML data format, so we had to adapt the read PLM XML model just to read their data quite straight. And again, we start with the first visualization just to give the researcher a first view. It did a lot of investigation in the data sets, and on the right side you can see, for example, this was a problem we investigated, and these were the first steps of a simulation we did. Like you can see, for example, this is the back of a server rack, and on the other side, of course, there's a front, and in the front goes the hot air, which is going out in the back, just around the rack, and on the other side going inside the rack. So there's some problems because this is not wanted behavior of the air conditioning system. So the air conditioning is not working properly in this setup. We started to simulate it regular. But as I said, the model has to be refined a little bit to do a better simulation. Yeah. Again, continuing to investigating the air conditioning system, you can see Uwe is navigating to the air conditioning system, and you can see, for example, a little bit better behavior of the air conditioning system, just getting the hot air separated from the racks and just going through the ceiling and in the cooling system.
On axial clone, what is the size of the cyclone? Because when you have the visualization, it seems to be a huge thing. So I didn't figure out at the beginning. It seems to be huge. It's clearly this size, or it's smaller, and it's just for the purpose of the analysis that you had a big view.
Of course, the right image you can see over there, it's too big in visualization. This is quite a correct size of the model.
Okay.
So this is turbines have also the tubes going through to the turbine have a diameter of about, I think this was 80 centimeters to a meter.
Okay. Did you try with your guest to change the visualization scale in order to see the phenomenon from another point of view, or is it not interesting to do that? I imagine when I see that, maybe you can play with the scale for the analysis, no?
Yes, of course. We are going, so we can change the scale, as you see here.
Yeah, clearly.
Quite on the fly, just going through details, and we saw right away, after a couple of minutes in the scene, we saw first problems with the geometry. So there were some edges in the geometry in the separator. You cannot see them here because we made fine photos, not the bad one. So there was in the separator some kind of edges where the water flow has to go through, and so these edges are very bad for the design because there are turbulences behind these edges, and they have just, this was a small error in the geometry for the model, I think, so they had just to change the geometry for the simulation.
Okay, but maybe we can say that the result is a multi-scale interactive visualization allow to see things they would not have seen otherwise.
Yes.
Oh, so it's very important.
Yeah.
I have another question. On the next one, you said we developed PLM XML. What is that? Yeah. For curiosity.
So PLM XML files, so this is a file format, for example, used by Siemens PLM
Okay.
So this is an tool, an PLM tool, Product Lifecycle Management tool,
Yes.
which is using XML format to describe, for example, geometry,
Okay.
and to reference, for example, VRML files in that geometry, but the format is enhanced with more data, so you can add all the PLM data inside that. So
Okay.
basically, this XML files just describes which VRML files are located where in space, so that our software can just place, for example, one of the rack at the specific position in the space, and then describing where are the inlets, where are the outlets, and what is the rack about, how many power does it consume, what load is it driven, how many CPUs, and so on.
And this is specific to Siemens?
First of all, it is open, so
Okay.
there's a description of the format, so it's text, ASCII text-based, and yeah,
Okay.
so Siemens PLM is using it.
I will look on the web. Thank you.
Yeah. So you can go for, if you are interested in that project, by the way, you can go on the website coolmall.eu.
The simulation core, which is behind this temperature deviation simulation, was that part of the Cool project, or did you use an existing simulation tool to do this simulation?
So the simulation tool is part of the Cool project. Actually, they are using the simulation tool OpenFOAM, or the data format OpenFOAM. So this was quite easy to use OpenFOAM. Yeah, the mesh generation was a little bit complicated, but we were free to use OpenFOAM to do the simulation on our visualization cluster. So we need no licenses or something like that. But as far as I know, current state is not clear in that project that they are continuing using OpenFOAM because some numerical experts are criticizing OpenFOAM, and I don't know the details, I'm sorry. But we did it in OpenFOAM.